Hey folks, this is the solutions to the last couple of homework questions that I got for Unit 3. These are all from the Unit 3 review section at the end. The first one is number 17A, and it says determine the solution to the system. So here we actually have kind of more equations than what we might expect. Normally, we'd say, is there a solution to 3 planes, and do they all intersect in a point? And now we have 4 planes, which is kind of too much information in some ways. But what we're going to do is basically say, do these intersect? Now, if they intersect in either a line or a plane, so just added in some diagrams here. These are the 2 ways that those 3 planes could intersect. And then if they do intersect in one of those 2 ways, either in this line of intersection or a point of intersection, so they could, just kind of highlighting this here, they could intersect in a single point like case 8, or they could intersect along that line. If we throw in now a 4th plane, if they intersect in this line, that 4th plane could kind of go anywhere like that, and there would be a point of intersection of that line with plane 4. And if they intersect in a point, we will want to check if, this is going to be kind of messy to draw, like if plane 4 also intersects across that same point. So first of all, we're going to look at the 3 equations there, see if they have an intersection, and then if they do, if they intersect in a point, we're going to check the point and see if it's on that 4th plane. And if they intersect in a line, these first 3, then we will check and see where that line intersects with the 4th plane. I guess one other thing we should really make sure that we check is that none of these planes are parallel or coincident, and no 1, 2, 1 is that normal, 2, negative 3, negative 1, 3, 5, 4, and 4, 1, 1. So I don't have any scalar multiples there. So I'm just going to solve the system created by the first 3 planes. Again, totally for now anyway, ignoring that 4th plane. So luckily I had that 1 in the top corner already. So I'm going to clear out that rest of the column here. For row 2, I'm going to subtract 2 times row 1. And for row 3, I'll subtract 3 times row 1 because of those coefficients. So the first row does not change. Second row, 2 minus 2 times 1 is 0. Negative 3 minus 2 times 2, so negative 3 minus 4 is negative 7. Negative 1 minus 2 times 1 is negative 3. 6 minus 2 times 1 is 4. And then the next row, I have 3 minus 3 times 1, which is going to be 0. Then 5 minus 3 times 2, so 5 minus 6 is negative 1. 4 minus 3 times 1 is 1. And 5 minus 3 times 1 is 2. Now the next thing, I want to get a 1 here, and I really, really don't want to have to divide that mess by 7, but I do see that I've got a negative 1 there. So I'm going to kind of do a little bit of a tricky thing here, because we can swap the order of the rows. So my row 2 is going to be -1 times row 3. I'm just kind of switching that row 3 up to row 2 and multiplying through by a -1. So that one was a much easier kind of thing to get a 1 in that position. So from here, I'm going to clear out row 1 normally. So I'm going to do row 1 minus 2 row 2. And always, if that's below, that's referring to the new row 2 there. So here I have 1 minus 2 times 0 is 1. And then 2 minus 2 times 1 is 0, which was really the point. 1 minus 2 times -1. So minus 2 times -1 is plus 2, and 1 plus 2, that puts a 3 there. And then last one, I have 1 minus 2 times -2, so that would be 1 plus 4 is 5. And now I'm going to say that row 3 is going to be row 2 plus 2 times the new row 2. So this notation gets a little bit weird because I'm going to take this row, which is now going in here, and you can do this in multiple steps to just kind of swap the rows in one step and then clear it out, but I'm just trying to save some space. So in any case, I'm going to do this row plus, oh, not 2 times, 7 times, because I have a -7 there. So I'm doing this row here plus 7 of these ones. So 0 plus 7 times 0, easy peasy, that's 0. -7 plus 7 times 1 is 0, which was the whole point. -3 plus 7 times -1 is -10. And 4 plus 7 times -2, 4 plus -14 is -10. And then we see, oh, that's so much nicer to divide that out. So if you ever have a number that you think, oh, I do not want to divide, always see if there's a way you can switch the rows instead. So I think we'll be able to get a pretty nice answer here. Of course, the first thing we're going to do is get a 1 there, and I'll just divide out a -10. So that's row 3 divided by -10 is 0, 0, 1. And then for row 1, I'll say that that's, I'm just going to be subtracting row 1 minus 3 row 3s to clear out that 3 in that position. So here 1 minus 3 zeros is 1, 0 minus 3 zeros is 0, 3 minus 3 times 1 is 0, and 5 minus 3 times 1 is 2. The last one, row 2 plus row 3, because I've got a -1, I just have to add that one in. So when I add the green row 2 from the previous step to the new row 3 over here, what will I get? 0, 1, 0, and -1. So the POI, it ends up that this is this case here. The POI is 2, -1, 1. I'll just add a slide in here. So we're going to check 2, -1, 1 in plane 4 and see if that intersects. So plane 4 was 4x plus y plus z equals 8. And we'll just do a left side, right side check. So 4 times 2 plus -1 plus 1. So 8 minus 1 plus 1. And that checks out. So here we can say, therefore, the POI of the 4 planes is 2, negative 1, 1. If it had not checked out here in the fourth plane, then the intersection of all four wouldn't exist. There would be 3 of them intersecting in a point, but the fourth wouldn't go through there, so there's no solution if we hadn't gotten that left side, right side check in the fourth plane. Okay, so here we've got 3 planes with these equations do not simultaneously intersect. So we can see from the normals that none of these planes are parallel, and they're telling us ahead of time they don't intersect. So that would be, I will just grab that picture. That's going to be the case where they all intersect in lines and it kind of forms like a triangular prism. So that's what we have. We have 3 planes and they don't all intersect simultaneously, but they're going to have lines of intersection. So I'm going to label the planes 1, 2, and 3. And basically what we're going to do, we're going to find the line of intersection of 3 pairs of planes. So we're going to do 1 and 2, and then I'm going to need some more slides for this, but I'll do 1 and 3, and then 2 and 3, and we'll look at the equation of each of those lines. So let's find the intersection of plane 1 and 2. Remember, we always start with that because there's an infinite number of possibilities for the vector equation of that plane. And we're just going to randomly, not so randomly, pick the one where we have an z component of our position vector. So the point on the line is going to be the point on the xy plane. And the z component of the direction vector will be 1. And that just means that that's the direction vector is the scalar multiple where there's a z of 1. It just, again, makes our math easier. So here, the first equation, I have 3x plus y plus 7t equals negative 3, just kind of bringing that over and getting ready for elimination. And the second equation, 4x minus 12y plus 4t equals 24. Now, to do elimination, I need to get rid of the y or the z, so I'm going to multiply that first equation times 12 and say that that is going to be 36x plus 12y plus 84t equals negative 36. And then I'll add these down in this column. So here I get 40x, the y's would reduce, and then I've got plus 84t equals negative 12. So x is going to equal negative 12 over 40 minus 84 over 40t. And we can reduce that, make it a little bit nicer. So x equals negative 3/10. Certainly a 4 will divide out of there. That'll be minus 21 over 4t. So that gives me the x component of the position is negative 3/10, and the x component of the direction is negative 21 over 10. I divided by 4, but then left the 4. So negative 21 over 10. We're going to use this x and our y equaling t to find, just scoot that up there, to find the y value. And from that first equation, I'm going to say y equals negative 3x minus 7t minus 3. And then I'll put in the values of x here. So y equals negative 3 times negative 3 over 10 minus 21 over 10t minus 7t minus 3. So I get 9 over 10 plus 63 over 10t minus 7t minus, I'm actually going to common denominator because I don't have a calculator with me, so we're doing this all in our heads. That'll be 70 over 10 and 30 over 10, like that. So here I get negative 21 over 10 minus 7 over 10t, and that's my y. So what we're trying to prove is that we're going to have the same direction vector or a scalar multiple of that direction vector for each of the 3 pairs of lines. So going into, I'm going to need to make another slide. I'm going to do this whole process again to find the intersection of, let's say, line 1 and line 3. So here I don't want to use a t again, just to not repeat the same variable. I'm going to say let z equal m. So line 1 is 3x plus y plus 7m equals negative 3. And then line 3, or plane 3, pardon me, I have x plus 2y plus 3m equals 4. Now, I could multiply this first one to eliminate the y's. I'll multiply that by 2. So I get 6x plus 2y plus 14m equals negative 6. And then I'm going to add down, subtract these equations to eliminate that. So I get negative 5x minus 11m equals 10, and then x equals 10 plus 11m, and these are over negative 5, and x equals negative 2 minus 11 over 5m. So when I get to this point, I actually had to just pause this for a minute. I know that I've actually made a mistake somewhere, and I've gone and found it, because I had my z values like that, and now I get an x for my position is negative 2, and for my direction is negative 11 over 5. So when I saw this negative 11 over 5, I panicked for a little bit and thought, oh, that's not right. One of these is not right, because this should be the same or a scalar multiple of the direction vector of the other line I just found. So I went back to the other slide, and I've already corrected it, because when I was doing the elimination here, I did 4 plus 84, and I just wrote an 84. So that was my mistake. I've changed that to 88 because I promise I can add, and corrected that, kind of followed it through. It changed the values for the y as well. So back on track, and then it did actually have the same x component, which is good news. Now, I'm going to again figure out what y is, and I'm using that first equation just because it's easy to solve for y. So y is negative 3x minus 7m minus 3, and if I know x is negative 2 minus 11 over 5m minus 7m minus 3, so here I get 6 plus 33 over 5m. I'm going to make that minus 35 over 5m minus 3. So here I get 3 minus 2 over 5m for my y. So the position vector component for y is a 3, and the direction vector is negative 2 over 5. So you can see now that I corrected the first equation, if I added properly, that we have the same direction vector for both. And then the last one, we'd have to do just the same thing all over again. You guys can try this on your own, or I'll just try to go pretty quickly through this. We would look at line 2 and 3. So here I've got, I'm going to say let z equal n. And my position has a 0 and then n. And I've got a 1 there. So I'm looking at the second two equations, 2 and 3. So here I have 4x minus 12y plus 4n, just any parameters, equals 24. And then I've got x plus 2y plus 3n equals 4. So I can do any multiples of these. Why don't we try eliminating the x this time? I'll multiply that by 4. So I get 4x plus 8y plus 12n equals 16. And I'll just rewrite the previous one just so they're lined up nice. 4x minus 12y plus 4n equals 24. So then adding down, or subtracting, pardon me, because I've got same signs. Careful with your double negatives. When I subtract here, I have 8 minus negative 12, so that's 20y plus 8n equals negative 8. And then solving this for y, I get y equals negative 8 minus 8n, and dividing a 20 by both of those. So y equals negative 2 over 5 minus 2 over 5n. So the position vector doesn't really matter. That's just where it crosses the xy plane, but the direction vectors should all be the same. So I'm already kind of like looking back and saying, oh, good, because I wanted to have that negative 2 over 5 in that component. So using that third equation, x is negative 2y minus 3n plus 4, and I'll just sub in my value for y. So x equals negative 2 times negative 2 over 5 minus 2 over 5n minus 3n plus 4. So that's 4 over 5 plus 4 over 5n. And I'm going to get a common denominator and go ahead right here and say that's 15 over 5n plus 20 over 5. So 24 over 5 minus 11 over 5n. So that, I can fill those in. So we can say, therefore, the direction vectors for each line of intersection are equal, and maybe specify that those are your direction vectors that you're talking about. Therefore, they are parallel. And then the last question that I think I have here, this is kind of a nice conceptual question. The actual math behind it, not too tricky, but it's kind of testing here whether you really understand what's going on with the relationships between lines and points and planes. So I have a plane here, and I have a point in space somewhere called x, and we're going to draw a line perpendicular to the plane, and that line is going to meet at point M. So I'm going to draw this line going down perpendicular to the plane, and somewhere on the plane is point M, and that's perpendicular. So when I have the equation of a plane in Cartesian form, we all know that that is the normal So the normal to this plane is 4, negative 5, 1. And if we want to find, I drew this kind of as a line segment, but let's say that that line could keep going for forever. The equation of the line, we have right here, we have a point and we have a direction vector, because the direction vector of this line that's perpendicular is just the normal of the plane. So the line, we can find the equation is r equals the point, so my position vector that I'm given, plus a scalar multiple of the direction vector given by the normal of the plane. Now we want to know where this line crosses this plane. And remember, to find intersection of a line and a plane, we put them into parametric for the line. So x is 3 plus 4t, y is 2 minus 5t, and z is negative 5 plus t. Then we simply take these expressions, sub them into the equation of the plane, and solve for t. So 4 times 3 plus 4t minus 5, I should have not written that right smack dab in the middle. That's okay, we'll squeeze it in. 2 minus 5t plus negative 5 plus t minus 9 equals 0. So here I have 12 plus 16t minus 10 plus 25t minus 5 plus t minus 9 equals 0. So how many t's do I have? I have 16 plus 25 is 41 plus one more, so I have 42t. And then 12 minus 10 is 2, minus 5 is negative 3, and minus 9 is negative 12 equals 0. So t is 12 over 42, or we can divide out a 6, 2/7. So then we'll just take this 2/7 and sub it into those expressions. So I am going to actually just pop to the next slide, just so you don't have to cram this in. So x is 3 plus 4 times 2/7. Y is 2 minus 5 times 2/7. And z is negative 5 plus 2/7. So we can get each component. And I have lost my calculator, so I'm showing all of my steps to try, not to make any silly mistakes here. So the point M is 29 over 7, 4 over 7, and negative 33 over 7, because that t value tells us how many multiples of the normal we have to take from x to get to point M where it intersects.